Pluto is a faraway and unpretentious yet seriously genuine planet that was once a part of our nearby planetary system. However, groundbreaking statements by leading astrophysicists Neil deGrasse Tyson and Kaku have brought Pluto back into the spotlight. They have suggested that this distant world is on a potential collision course with Neptune. But how could this actually happen? Additionally, what might be the consequences of such a massive event? Are we witnessing a perplexing astronomical eccentricity, or is there something more to this impending cosmic catastrophe? Join us as we examine the scientific implications of a Pluto-Neptune collision. The Pluto-Neptune collision hypothesis. Pluto, a former planet that was reclassified as a dwarf planet, remains a subject of great interest in the vast universe. According to recent predictions by leading experts, Pluto's orbit is dangerously close to Neptune's. Astrophysicists Neil deGrasse Tyson and Kaku are both raising the alarm about a potentially catastrophic collision between these two celestial bodies, an event that could have significant repercussions for Earth. But how is such an event even possible? Pluto's journey around the Sun is unlike that of any other planet in our solar system. It takes an astonishing 248 years to complete a single orbit. Since its discovery in 1930, it has yet to complete one full revolution. However, the intrigue doesn't stop there. Pluto's orbit is characterized by its highly elliptical shape, which deviates significantly from the nearly circular orbits of the major planets. What makes Pluto's orbit even more unusual is its inclination, tilted at 17 degrees relative to the ecliptic plane. Compared to the other planets, Pluto follows a much more unpredictable path. This inclination and eccentricity add layers of complexity to its orbital dynamics. One of the most fascinating aspects of Pluto's orbit is its interaction with Neptune's. For nearly 20 years in each orbit, Pluto actually moves closer to the Sun than Neptune, contradicting what we might expect from their positions in the solar system. This leads to a fundamental question. Why hasn't Pluto collided with Neptune? The answer lies in gravitational interactions. The answer lies in the gravitational influences of other planets. The study of Pluto's orbit began shortly after its discovery. Initially, astronomers struggled to understand its unique trajectory. Unlike other planets, whose orbits generally align closely with the ecliptic plane, Pluto stands out due to its steep inclination and irregular shape. The mystery deepened when scientists realized that Pluto's orbit does, in fact, cross Neptune's. The fact that Pluto's orbit remains stable despite these complexities is a testament to the intricate nature of celestial mechanics. The three-body problem in astrophysics involves predicting how three objects in space, such as Pluto, Neptune, and the Sun, move and interact under the influence of gravity. It's like trying to predict where they will go based on their starting positions and the gravitational forces pulling them. In Pluto's case, this problem illustrates how its orbit, Neptune's orbit, and the Sun's gravity all interact in a complicated way. Several key concepts explain this dynamic. 1. Non-synchronous libration. This term refers to the fact that when Pluto crosses Neptune's orbit, it is positioned at least 90 degrees away from Neptune. This spatial separation prevents their orbits from intersecting. 2. Orbital precession. This refers to the slow, cyclical movement of a celestial body's orbit. For Pluto, this means that when it comes closest to Neptune or another giant planet, it is positioned well above their orbital plane, adding an extra layer of protection against potential collisions. 3. VZK wobbling, named after three scientists, Zell, Kai, and Kaku. This concept describes how gravitational interactions among three celestial bodies, Pluto, Neptune, and the Sun, influence their motions. This phenomenon explains why Pluto's orbit appears chaotic but is actually stable over long periods. Despite Pluto's orbit seeming erratic, this wobbling helps maintain its smooth motion over extended time frames. The VZK wobbling effect demonstrates that while space may appear chaotic, underlying patterns and gravitational interactions help maintain order. The stability of Pluto's orbit. This three-body problem is crucial to understanding how planetary orbits evolve due to gravitational influences. Studying it helps scientists learn more about Pluto, our solar system, and even distant galaxies and their stars. Mathematical simulations in the late 1980s revealed that, despite its stabilizing properties, Pluto's orbit is highly sensitive. Small initial deviations can lead to massive changes over millennia. However, these characteristics have been found to maintain stability over extraordinarily long timescales. Modern automated simulations have helped scientists understand how giant planets like Neptune, Jupiter, and Saturn influence Pluto's orbit around the Sun. Neptune and Pluto share a unique orbital resonance. For every 2 orbits Pluto completes around the Sun, Neptune completes 3. This gravitational relationship helps stabilize Pluto's orbit. However, Neptune isn't the only factor at play. Jupiter's immense gravity also plays a major role in maintaining Pluto's trajectory. Saturn, too, contributes to this gravitational dance. The role of Jupiter and Saturn. Studies show that Jupiter's powerful gravity is strong enough to keep Pluto on a steady path for millions, perhaps even billions, of years. This suggests that Neptune alone isn't the deciding factor in Pluto's stability. Instead, the combined gravitational influences of multiple giant planets act as a safeguard, ensuring Pluto doesn't veer off course or collide with Neptune. So, while Pluto's orbit may appear chaotic, it is, in fact, governed by complex but stable gravitational interactions. This means that, for the foreseeable future, a Pluto-Neptune collision remains highly unlikely. Jupiter and Saturn are planning to guarantee Pluto keeps on moving securely through space without running into inconvenience. These eccentricities are vital for keeping everything set up. Without these components, the nearby planet group, as far as we might be concerned, would be a much harsher spot. Bodies like Pluto could collide with others or be catapulted from their consistent circles, setting off a chain response with other divine bodies. For Pluto, especially with worries about it perhaps colliding with Neptune later on, understanding its circle is fundamental. This gives a more clear image of the powerful idea of the nearby planetary group. The instance of Pluto demonstrates the way that even the most apparently shaky circles can arrive at a condition of balance through the perplexing collaboration of gravitational powers and orbital mechanics. It likewise highlights the significance of steady perception and examination of these quirks to all the more likely comprehend our spot in the universe. Exploring the profundity of room frequently compels us to defy the strange idea of divine bodies. Pluto's circle is an ideal illustration of this peculiarity. The idea of orbital confusion, which alludes to the fragile dependence of a heavenly body's circle on its underlying circumstances, is obviously exhibited. For Pluto, this implies that even slight changes in the Bantam planet situation or speed can radically modify its drawn-out circle. Utilizing mechanized reenactments has been gigantically useful for specialists in sorting out how Pluto moves in space. These reproductions utilize complex science to display how Pluto and other space objects, like Neptune, pull on one another. By tweaking little subtleties in the recreations, space researchers can perceive how even moment changes can make an immense distinction in where Pluto winds up. In the last part of the 1980s, these reproductions showed something intriguing about Pluto's circle. Regardless of having highlights like non-concurrent libration and orbital precession to keep it stable, its orbit can in any case be conflicting and uncommon. On the off chance that you start with just a little contrast in where Pluto is or how fast it's moving, its circle could wind up looking totally different after only a couple of years. Yet, in spite of this disorder, Pluto's circle stays stable throughout colossal time scales, like billions of years. This implies that Pluto's excursion around the Sun has a sort of request to it, despite the fact that it shows up wild at first. Foreseeing heavenly developments, especially when they involve sporadic circles like Pluto's, presents an enormous challenge. The innate irregularity of these frameworks implies that long-term expectations are often filled with uncertainties. While numerical models provide brilliant tools for understanding and predicting the future movements of heavenly bodies, they also highlight the limitations of our predictive abilities. These models heavily rely on the precision of initial conditions, and any small error or distortion can lead to vastly different outcomes, making accurate forecasts a daunting task. Beyond the tumultuous nature of planetary circles, Pluto reminds us of the ever-changing and dynamic nature of the universe. While we've made significant progress in understanding space, Pluto's case serves as a reminder of how much remains unknown. Grasping the gravitational effects of the giant planets on Pluto's circle provides valuable insights into the broader dynamics of the planetary system. It demonstrates that the presence and position of each planet can significantly influence the stability and trajectory of other bodies within the system. So why are leading astrophysicists recently raising concerns about a possible collision between Pluto and Neptune, despite all these intricate forces working to prevent such an event? Neil deGrasse Tyson, a prominent astrophysicist and a major figure in advancing cosmology, offers a unique perspective on the mysteries of our planetary system, particularly the fascinating case of Pluto. Tyson, known for his role in reclassifying Pluto from a planet to a dwarf planet, provides insightful analysis on the evolving nature of celestial mechanics and the public's interest in the forgotten corners of space. Tyson's stance on Pluto's renaming is based on our ever-growing understanding of the solar system. He sees the reclassification not as a demotion but as a necessary adjustment to our developing comprehension of the various bodies orbiting our Sun. His approach to celestial mechanics is one of constant learning and adaptation. He views the complexities of orbits like Pluto's as a sign of how much there is still to discover in space. This curiosity keeps the study of astronomy so exciting. However, despite Tyson's optimism, his thoughts on Pluto's potential collision with Neptune paint a different picture. His concerns about Pluto's fate stem from his understanding of the unpredictable nature of these orbits. Tyson acknowledges that while Pluto's orbit has remained stable so far, small shifts over time could lead to catastrophic events. Pluto's trajectory, particularly its resonance with Neptune's orbit, is a delicate cosmic dance that might remain stable. Yet, in Tyson's view, even slight disturbances in Pluto's orbit could have significant, long-term effects. If these shifts accumulate over millions of years, they could eventually result in a more unpredictable outcome, potentially even a collision with Neptune. However, such events wouldn't happen anytime soon. Rather, they would unfold over vast time periods, far beyond human lifetimes. Nonetheless, Tyson's cautious stance underscores the importance of continued observation and understanding of Pluto's orbital dynamics. Tyson isn't alone in his views. Michio Kaku, a theoretical physicist, also contemplates the potential chaos that could arise from planetary interactions within the solar system. While Kaku shares Tyson's enthusiasm for exploring the wonders of the universe, he also recognizes the inherent instability of planetary orbits and the unpredictable effects that could emerge over time. Both Kaku and Tyson emphasize the importance of ongoing research into the forces governing planetary motion and the future of our solar system. Ultimately, the case of Pluto serves as a reminder that our understanding of the universe is constantly evolving, and new discoveries often raise more questions than answers. As astronomy continues to advance, the possibility of an event like a Pluto-Neptune collision reminds us that space is full of surprises. The seemingly stable orbits of planets can be subject to dramatic changes in the future. These reflections on Pluto highlight the importance of keeping our eyes fixed on the stars and our minds open to the mysteries that still lie ahead.